I do that right? Okay, and then I just need to add in. Do you know which number it was by any chance?
A 29.
Toward the end. Okay.
If you uploaded it, we got it.
Okay, is this it?
Yeah.
Okay.
Exactly. You uploaded it.
Okay.
Fine, yeah. You downloaded it.
Okay.
Yeah, should be all set.
Okay. You get it in by the.
We got it all, yep. Yep.
So far you have our area.
Yeah, I think we got it all.
Okay. Because you had.
All good? Okay, cool. Yeah.
Yeah.
Are we updating something?
Yeah, it shouldn't affect you at all. It's for posters.
So I don't want to make sure everything's fresh.
Yeah. No one's trying to hack in.
Might be mad because I have this. You know what? It's not. Yeah.
We got them, what, within the past hour?
Alright, cool.
We got it.
Yep.
Okay.
What's the first?
Yeah.
This is all on, and then is Elise good with her setup?
Elise, are you good with the live stream?
Okay. There's been a poster update, so.
I mean.
Okay, it's just Monday afternoon.
Yes, and
Okay.
yeah,
Are you doing Tina? Just spectating?
and none of the presentations have been changed, so we'll just leave
Okay,
it the
so
way it
there's
is.
just a poster that has to be
Yeah,
changed.
but like I'm
Okay.
just gonna leave it because she had a poster there before. Yeah,
Okay.
it's just she made an update, so it's fine. Yeah.
For all 5 people watching the live stream.
Okay. Is the live stream going?
Yes.
Okay.
I am.
Yes. Also,
I'm
you
gonna run
missed
to the bathroom.
Danielle's announcement that he was like, "Don't leave any of your stuff in here."
And I did.
Well, I was like, I saw that, and I'm like, "Oh,
I didn't even.
you left your stuff," and then I saw it was yours. I'm like, "Oh, well, it's
I
fine."
didn't. It was an accident. I like got to the law school and I was like, shit, I don't have my stuff. Bathroom. Anybody need anything?
One of the bathrooms there had a bunch of water all over the floor.
Great. Maybe I'll go upstairs.
I would say for you guys tomorrow, definitely like, do you feel comfortable putting together the 30-second slide intro thing into one PDF by yourself?
I think so. Makoto, I think, knows more about your download thing.
You can do it however way you want.
Yeah.
I just was doing it in preview.
It's annoying regardless.
Excuse
Yeah.
me, I'm the first talk.
Okay.
Can I have tried the
Just be aware it does take time. So like definitely something you have to prep through lunch.
Okay.
My field trip starts at 1, so
Okay.
I'll definitely be gone by then. And also, you're fine to saying, like, if people come up to you and you don't feel good, just you can say no.
Okay. Were you okay with this?
Yeah, like, my thought is, like, I knew we had plenty of time, so I was like, I'll try to push back, and if they, like, still, then
Yeah.
I'll, like, okay, let me try. If it works, like, in a reasonable amount of time, I'll do it.
Hey Makoto, could you? Sorry.
Yeah.
Could you just?
Speak into it.
Yeah. Let me get my. Sorry, one sec. Let me get my. Nope, this has got the wrong speaker.
Sorry, no.
Maybe it's just. Makoto, could you try speaking into the?
1, 2, 3. Go there. 2, 3.
It's definitely doing it here.
Yeah, it says it's going. No.
It's definitely doing it here.
No.
It's coming in this speaker, not that one. Is that? We can try. Do you want to try unplugging it and plugging it back in?
Yeah.
No, it's coming in this speaker, not that one. We can try. Do you want to try unplugging it?
Oh, I'm whispering. Just listening to it.
Hello, hello.
One, two, three, test. 1, 2, 3, test. Yeah?
Yeah. Awesome. I had that my first year. Had that happen where like I was in the overflow room and I didn't realize like my phone was on and I was sleeping on the computer. Said something and I wished. No, I'll do okay. I'm just going to the computers.
Hello.
You don't have to plug or unplug anything.
This one is.
It goes to sleep really fast. I think it's just asleep. But also the logins are both. So you just like put that on.
forgot Makoto and I said we were gonna put it so it didn't sleep so fast. But
Okay. Great. So they're all just here. Is there like a folder?
probably just Monday afternoon. Yeah.
Great. And you have an agenda with which is which?
Yeah. Do you want? I already wrote it on mine. Do you want to just borrow mine?
Yeah. Or I can just wrap.
I've looked for it so many times. Like very soft enough. Chickpeas, potatoes, broccoli. But like when you go back on the video, it's a button. Like this. Yeah.
That's correct.
That's but see it's already on H2 even though I didn't say it. Because that's like the automatic go-to one. So like some of you have to flip off of it to flip back onto it. It's really annoying.
Got it.
Yeah, I mean, I think it's, I think that's, so I think it's trying to
Testing, testing.
yeah, that's right. Yeah, I think that's. Whatever he says. That's so fun. Finally, something's gonna. I can't believe it.
Like if people submitted like their certain things as you just go and check, they should have, if they're not doing anything, just make sure that they don't like, they don't want to work, like they have a dongle. And if they don't, try to find one. Yeah. Yeah. I mean, like, try asking like each other, like just talk. Like, I have lots of it depends what the average is. Like all I said you did great sharing. You were the picture of calm. Even though factors outside of your control. At least yeah. So you were doing, I just did one and you did the two check I usually 6 minutes too early. One Yeah,
Thank you for doing this. So I think it's
All right, we're gonna get started. Yeah, that sounds awful. Is that better?
Yeah,
Yeah.
actually, we gotta make sure people stay some distance
Okay.
from the mic.
We're gonna start regardless of whether you're sitting down. All right, our first speaker will be Hanson from the University of Colorado. I will put up the 1 minute for those of you speaking. Just like Eloise, I'll put up the 1 minute at 6 minutes.
Hello everyone, I'm Hanson Cao from CU Boulder. Today my topic is inverse modeling constraints on sources of ammonia using CRIS measurements. As we all know that current bottom-up estimates for ammonia is quite uncertain, and the satellite observations can provide us top-down constraints on ammonia emissions with up-to-date information and greater spatial coverage and continuity in time. And there are currently several satellite instruments monitoring ammonia in the atmosphere. Schiffer 2016 used Yazi ammonia column to constrain geochem column and explore the driver of this internal annual variability. And most recently, Zhang 2018 used test ammonia to optimize Chinese agriculture ammonia emission, and found that current bottom-up emission inventory generally underestimate the summer peak in agriculture emission for China. So here, and now we have the most fresh CRIS ammonia product with greater spatial coverage and smaller noises, and with larger amount of data set. And here we use the daytime CRIS ammonia profile to optimize the ammonia emission for contiguous US for each month in 2014. CRIS is an infrared sonar on board some synchronous satellites. Its nadir resolution is 40 kilometers, and it achieves global coverage twice a day. To start our inversion, we firstly use the a priori ammonia emission to drive the geochem forward model at a quarter degree for contiguous US domain. And then we compare the geochem ammonia profile against the CRIS observations, and the difference between model and the CRIS is propagated backwards through geochem Asian model, and the difference is iteratively minimized by a quasi-Newton method. First, let's take a look at the CRIS surface ammonia in 2014. As we can see that CRIS ammonia is higher over known agriculture areas during warm months, and the GC a priori, the geochem simulation driven by our a priori emission generally capture the spatial pattern and the seasonal variability observed by the CRIS, but underestimated the magnitude, especially over warm months. And after the emission optimization, the GC a posteriori better reproduce the CRIS observed magnitude and seasonal variation of surface ammonia. Similar improvement can be found when we compare the vertical profiles of GC posteriori against the crease measurements, especially during the warm months. And then let's take a look at the difference between the posterior and the priori emissions. The top panel shows that the posterior ammonia emission has a similar spatial pattern as the priori emission, and the top panel shows that the increase can be found across most of contiguous U.S. Except there is some slight decrease over Iowa and southern California. We then use the monthly mean AMON measurements to validate our GC a priori ammonia. As you can see that our GC posterior surface ammonia largely improved when you see the correlation when you see the regression slope. The regression slope increased a lot and much closer to 1, and the R there is slight change in the R. We also checked the correlation coefficient between the monthly mean GC simulation and the AMON measurements side by side. As you can see, the priori R is quite low and even negative over the eastern US, and after the emission optimization, the posterior R increased over central and eastern US. And also the crease-derived ammonia emission enabled the model to better capture the magnitude and the seasonal variability of the national average of AMON measurements with double the correlation coefficient and largely decreased normalized mean bias. So in summary, it's the first time that crease ammonia is used to invert ammonia emission over contiguous US, and the crease-derived ammonia emission enabled the model to better reproduce the seasonal variability of AMON measurements. And I'll leave my messages here and take your questions. Thank you.
So the fact that IASI is in the morning orbit and Chris is in the afternoon orbit provides an opportunity to recover potentially the temperature dependence of ammonia, or at least potentially the diurnal cycle dependence of ammonia emissions. Have you had a chance to look at the relationship between the ammonia columns derived from IASI and the ammonia columns calculated from Chris to see if there's a systematic difference that could be related to temperature?
Yes, there should be a temperature dependence, but I have never compared these two satellite products. Sorry.
So you compare your chem simulator with the satellite observation. Have you looked at the bias is just chem nitrate? So your own renewal, just chem plus the own acid and nitrate. Yeah. Then you test the kind of underestimate the ammonia concentration. Have you looked at how that will affect the emission? The nitrate play a role there.
Yes, we also simulate the nitrate, but we have never compared it against measurements. But we will do it next time, next step.
Okay, so I am Chi. I work with Randall on the project of assessing the refined difference mass balance and for derivative method to derive ammonia emissions over North America using synthetic observation. After such nice presentation of the previous speaker, Hansen, I don't think I have to convince you that the recently available PRIS observations are valuable for constraining ammonia emissions over North America. And she did that, use the standard 40VAR simulation system and adjoint model built to show that how well it worked to recover the observed ammonia concentration. It benefits from its advantage of accounting for the sensitivity of the differences between observation versus simulations against emissions at every location. But the only trade-off that is the large computation cost it has. If you're limited by computational resources, there is another option that we could separately do inversions at each grid cell, assuming that the local sensitivities of concentration versus emissions are more dominant comparing to the smattering effects from the adjacent grid boxes that contribute to the observed ammonia concentration. This might be reasonable for species that is short-lived, such as ammonia. There has a recent study from Matt Cooper showing that the NOx emission constraining at 2 by 2.5 degree resolution, the finite difference mass balance in the iterated manner could yield a similar inversion result comparing to the 40VAR simulation. And there has been an increasing interest about whether this also applies for ammonia in this CRIS community. To answer that question, we simulate pseudo-satellite or CRIS observation of ammonia concentration using geoscam, CRIS sampling date, and sensitivities from a assumed true ammonia emissions. And then we invert these pseudo observations to evaluate the performance of both methods. We evaluate the performance of the iterated finite difference mass balance using the adjoint as a benchmark. The first thing we found is that for the case of constraining ammonia emissions at 2 by 2.5 degree resolution, the finite difference mass balance also worked well relative to the 40VAR simulation. We simulated the inverse pseudo observations for 2 weeks of April 2013 using the regional emission inventories over North America. And we started our inversion using another different emission inventory. There is a giant difference between the two different inventories at almost every well, which has been substantially reduced after both inversion methods. There is no clear disadvantage of the finite difference mass balance in terms of both the domain-wide total biases in the emission estimates as well as the normalized mean errors. We also take a look at the normalized mean errors of the performance of the iteration at of the inversions at each iteration. And the real advantage of the iterative mass balance is that the simplified local sensitivities makes the emission adjustments at each iteration more aggressive comparing to the 40VAR, as represented by the more rapid error reductions, especially in the first several iterations. Generally, according to our test over 3 months in 2013, the finite difference mass balance generally needs about half less iterations and about 3 to 4 times less actual computational cost comparing to the 40VAR without sacrificing the final accuracy of the inverted emissions. So if you are interested in constraining ammonia at a scale of about 200 kilometers, we recommend you using the finite difference mass balance for its accuracy as well as its efficiency. So, but if we repeat these experiments at a much finer resolution, quarter degree, over a small nested region for Central North America with strong ammonia emissions, we find a contrasting conclusion suggested by our inverse test. Here we can see that the finite difference mass balance has some ability to reproduce the domain-wide ammonia emission in the assumed true emission. But the local and the normalized mean errors are much stronger comparing to the 40VAR results in our tests. And our test for the July and October cases consistently suggested the same conclusion. To extend this discrepancy of the performance of mass balance at different resolution, here we use the adjoint model to simulate the local ammonia the sensitivity of local ammonia column density versus the emissions at every grid box in our simulation domain for one ammonia emission source location at the quarter-degree resolution. Generally, from this graph, we could derive the smearing length of ammonia, and which represents the distance scale below which the cumulative emission influence increases rapidly with distance. Afterwards, it's going to be plateaued. And this distance scale matters for iterative finite difference mass balance. And our calculated distance scale is roughly 1 to 200 kilometers, which includes about only the local or just one adjacent grid boxes at 2 by 2.5 degree resolution. Meanwhile, this distance corresponds to strong smearing effects between hundreds of grid boxes at quarter-degree resolution, which the finite difference mass balance cannot account for. We could also derive a simple estimates of the smearing length using a typical lifetime estimates and wind speed over this region, which is also in the range of our calculated numbers. So this is another simple way to pre-assess if the mass balance approach would work for specific inversion tests. We also found that it is possible to do a two-step inversion framework by which to use the finite difference mass balance inversion at the quarter-degree resolution as the a priori emission inventory in the 40 var at a finer resolution. We found that the first initial inversion at quarter-degree resolution could also reduce the normalized mean errors at final resolution to some extent. And more importantly, such tests suggested that it consumes about 5 to 10 less iterations to reach the final products, also without sacrificing the final accuracy of the emission inversion results. The total computation time of this two-step inversion is still about 30% less comparing to direct inversion at final resolution from the original priori, suggesting a plausible way to combine the strength of efficiency from mass balance with the necessity of accounting for smearing in 40 var. That's all I want to share today, and I'd like to take your questions. Thank you.
So, the retrievals of ammonia from satellite are extremely sensitive to the vertical profile. And I'm wondering what kind of source of air that is in inversion for ammonia sources. And I'm also wondering what kind of air that implies for a plume transported downwind, which then mixes further up and therefore get more easily picked up by the satellite.
So in our test, it's a general methodology test without considering all these factors. Those factors are all the same in both inversions. For your question, if I understand it right, you're asking how the emissions at this site would contribute to the observation differences downwind, and inversely influence the emission result, inverting results. Is that right?
Well, considering that the plume would be lifted as it carries that down the wind, and therefore the satellite would be far more sensitive to that plume that's been lifted up than it was at the point of emission.
For the CRIS instrument, as far as I know, it's not actually more sensitive to above. Actually, it's quite sensitive to the boundary layer.
No, it has to be, because that's thermal.
There's some vertical.
That's very strong.
According to their evaluation versus the aircraft measurements, it seems to be more sensitive to the ground level, and it's relative to the thermal contrast of the surface, according to their description.
Okay, we're gonna move on.
Thank you.
And look, I got a microphone, so now I can introduce people from down here. So sorry to open on. All right, so Chiang is our next speaker, and.
Hi, I'm Chen Zhang from Tsinghua University, and today I'm talking about China's emissions. As we know, actually, the emission inventory dominates the performance of the model. So in China, as we know, air quality or air pollution in China has been changed, significantly improved during the last 5 years from the implementation of China's Clean Air Action since 2013. So the fast decrease of major air pollutants, including PM and other gaseous pollutants, actually can be linked to series of clean air policies since 2010, is specifically from 2013. So this figure shows how dramatically policies have been implemented in China during the last several years, from large industrial facilities to vehicles, as well as phasing out old and small combustion sources. So as a consequence, actually, we estimate that China's anthropogenic emissions has been changed dramatically in last 7 years. It's the changing rate is faster than ever before. For example, we had a very fast drop of SO2 emissions from around 30 million tons per year to 10 million, or even less than 10 million tons per year. So although we didn't run model by ourselves, but I guess it will has significant impact on the global atmospheric composition, as well as the, it maybe have immediate climate impact. So also primary PM reduced by around 30%, and 20% of decrease for NOx. In the meanwhile, the VOC and ammonia emissions almost keep stable, because actually there is an absence of relevant policies to those specific sources. So if we look into the detail of emission change by sectors, which sectors dominate the change, we can see actually for almost all pollutants, the decrease of industrial sector is very important. And the control of power plant emissions contribute a lot to the decrease for SO2 and the NOx emissions. And another signal is because if we look at the to a longer history, to 20 years, we know that the dramatic growth of activity rates and the productions and the vehicle populations actually stimulate the increase of emissions. But since 2010, with the slowdown of the economy, so those are the left part of the changes of activities, and the right part is the changes in emission factors. So actually, with the slowdown of activity rates, growth in activity rates, and the faster decline of emission factors, so combining them together, they driven the decline of emissions for those species. With one exception is VOC emissions. So VOC emissions keep growing since, total VOC emissions keep growing since 1990, back to 1990. And we look at the most recent years, actually, the residential sector and the transportation sector emissions were relatively, controlled. But from industry, both solvent use in industries and productions, they are still in increase. Because we do not have very active and effective emission standard and control measures on those emitting sources. When we look at the specific species, actually the aromatics, I think we need to pay more attention on this, because the aromatics is very active, both to ozone formation and SOA. And those largely from the industry and solvent use. Now is the largest group of species in VOC emissions. We also decomposite the changes to different species in different sectors. Really, if we look at the most recent several years, the aromatics from solvent use is the largest contributor for VOC emissions and maybe also ozone formation potentials. So from 2010 to 2017, actually with the dramatic change the magnitudes of emissions, so the size of the pie chart means the emission amount. Also the structure, so the relative contribution from different sectors also changed. So in 10 years ago, many of the emissions in China coming from large sources like power plants. But now we have almost all coal-powered plants equipped with low emission, ultra low emission standard. So its emission level is very low. So then more and more emissions are from small and scattering sources, which means more difficult to control. So last few slides, so when compare with our emission estimates with surface measurements and satellite-based measurements, so relatively we show consistent trends. And the last slide, if we look at the China's emissions in global inventory, one is seeds, usually in semi-precipitate, another is agar. Although they didn't have a very recent inventory to 2017, but until 2012 in agar and 2004 in seeds, they still estimate a growing trend in major China's emissions, so which might have different impact in global or regional models. So it should be cautious on that. Okay, I will stop here and let questions. Thank you.
So what is the outlook on VOCs going forward?
So from 2007, so in the second phase of China's clean action, so China's government aims to implement active control policies on VOC. But in the meanwhile, it's more difficult to control than SO2 or NOx because many of them from evaporate sources rather than. So we still expect it's still a big challenge on that. Maybe not growing, but we do not expect a fast decrease of VOC emissions than like SO2. It's much more difficult.
Yeah, can you just take one question? China too. Can you just repeat the question?
You're talking about the challenge in controlling ammonia emissions in agriculture, right? So actually, for the agriculture system, it's almost from the increase of fertilizer use. So those are very difficult to control. So in China, so the first phase of ammonia control goes to the the control of the cow or pig, so you can phase out the small and scatters farmers and to big ones. But for the fertilizer use, it's much more difficult.
All right, so our next speaker is Holly from Florida State.
Hello, I'm Holly Nell. I'm from Florida State University. I'm a postdoc with Dr. Christopher Holmes, and I'm going to be talking today about impacts of improved burnt area estimates on biomass burning emissions. This is based off some work we did last year along with 3 other co-authors that we published in Geophysical Research Letters. So what we were examining in the study we conducted was we wanted to look at fires in the Southeast United States. And it's a very important area to look at biomass burning because the Southeast United States actually on average burns half of all area that's burned in the contiguous United States every single year. In the state of Florida alone, we burn 10% of what's burned in the entire United States. And one of the reasons you don't really hear about it compared to out west is we just don't have wildfires in the Southeast United States. We have what are called prescribed burns, where we set fires on purpose for a reason, and it's usually to help with land management or agricultural reasons. And so we started looking at this because we know that satellite detection is very critical because you don't have a lot of good ground-based data. But there haven't been a lot of in-depth long-term validation studies that have occurred in this region, mostly out west. So we wanted to see how well are satellites detecting fire in this area. So we started using the state of Florida because the state of Florida has actually really good government records on burnings that occur. Because if you want to set a prescribed fire in the state of Florida, you have to get a burn authorization from the Florida Forest Service, and they keep track of that. And then we also have wildfire records from the Fire Program Analysis Fire Occurrence Database for all wildfire activity that happens throughout the state. So looking at this, we learned something, that prescribed fires are very dominant in Florida. That's why you don't hear this in the news, because over 92% of our fires are set on purpose. Only 8% of fires that occur in the state on average are wildfires. And the vast majority of the prescribed fires are what's called silviculture. So that's happening in forested landscapes. So it's usually done to help with habitat, to get rid of fuel that's gonna help wildfires spread. And we know that other southeastern states have similar characteristics because they have similar land cover types. They also use prescribed burn area heavily. So when we were looking into this, when we started seeing, okay, well, how well are satellites detecting these fires? We expected some underdetection. There have been some previous studies, usually smaller and not as long in duration, some case studies, that have also reported underdetection. And it's usually because prescribed fires are small, they're not very intense. Some only last a very short duration. I've been to some that have only lasted 20 or 30 minutes. They're very quick. They're hidden by canopy, and we have a lot of cloud cover. So when we started looking at it, we had our government reports right here, and we compared it against several different satellite databases. The main one I'm going to talk about today is the Global Fire Emissions Database, or GFED. That's the default biomass burning emissions in geochem. So looking at that, we determined that 70 to 80% of all fire area in Florida is not picked up by satellites or is underestimated. So that's consistent with the high end of past literature. So that's a very surprising result to see. So we wanted to look in a little bit more into this. Is there a way we can kind of correct for this bias? So we have over here on the y-axis what we're calling the bias. We have the actual fire area we know from our government records divided by the satellite detected area. That's what GFED is reporting. It's actually burned in that 1/4 degree pixel because GFED is on a 1/4 degree grid. And over here on the x-axis, GFED actually has a couple of different products. One product is a small fire estimate. So we are able to tell in each pixel about how much of that burned area came from what it's considered to be small fires versus large fires. So if a burned area in a pixel is almost 100% comprised of small fires, what actually burned on the ground is about 5 times more than what the satellite or GFED is reporting actually burned. So when you have a pixel over here, almost all of it occurred from big fires and there was no small fire component, only about 2 to 3 times more burned on the ground than what is being reported in the GFED product. So we know that similar detection biases are likely occurring in the other southeastern states, but what about beyond? Because Florida, unfortunately, we're not all beach. We have different land cover types, and this exists worldwide. So we went ahead and looked at the burned areas that occur globally according to GFED, and we applied that bias correction to be a scaling factor. And so we scaled up emissions based on the small fire percentage of each of those grid pixels. And what we found was that just looking at a couple of tracers right here, that global emissions could be 3 times more than currently thought from fire. So we wanted to go ahead and take this and put it into geochem. So we ran a couple of geochem models. The first one we call normal geochem right here. And that's just using GFED straight out of the box, not making any adjustments to it. And we compared it against station data from the Global Monitoring Division for CO on the ground. And this is a yearly composite or yearly mean during our study period. And then we did what we call the adjusted geochem run. We took it and we took that bias correction and scaled up those emissions. And so it's a little difficult to tell what's going on here. So we went ahead and created another graph. We divided the world into 30-degree latitude bins. And so in each latitude bin, we took the average of all the station data, and then we took the average of the pixels that match up with the stations. So it's not all the pixels that are included, it's just the pixels where the stations are located. And here on this graph, the numbers are the latitudes in the center of the bins. And notice that the scales are free. They're not all fixed to the same thing, so we can see this pattern right here. And over here is the average error, so you can kind of picture what that would look like with error included. And what we found in the Northern Hemisphere, we're getting improved CO estimates for the most part when we apply that bias or that scaling factor. But in the Southern Hemisphere, we're overestimating carbon monoxide. So it's kind of a mixed result. So important messages to take away from this is that, remember, fire area in Florida and probably the rest of the Southeast United States is grossly underestimated over a period of many years. When we apply size-dependent bias factors, we're getting 3 times greater emissions typically for CO and some other tracers. But when we scale up emissions in geochem, we're reducing the CO bias for the most part in the Northern Hemisphere. We're overestimating in the Southern Hemisphere. So this indicates that we need to do a finer treatment. We probably need to include fire types. Maybe Florida is not representative of savanna fires that you typically see in the Southern Hemisphere. And then duration, since prescribed fires are usually quick, maybe we need to do something with that as well to get a better estimate. So thank you. Yes.
So do you think that some of your overestimate could be due to the injection height because you're only surface observations?
It's possible. We only looked at the surface for this. So.
Yeah, I guess most of your fires were prescribed fires, and you got that based on permits.
Yes.
How realistic is it to assume that all the permits are used, and they're used for burning all the area that they get the permits for?
We actually, in the paper, I didn't have time to talk about it today, we compared some landowner records that they kept themselves against the database to assess how accurate it was. And we find that it's fairly accurate, but you do have days where the people decide not to burn. There's a tendency to overestimate because you don't want to get fined for burning more area than you requested. But for the most part, they tended to be fairly accurate.
Louise, you want to answer your question while you walk up?
Yeah. Do you have plans to evaluate the really high CO concentrations that you get in the changeover South America and over Africa using MOPIT or some other satellite project?
Yes, we just started doing this kind of analysis, so we have all kinds of plans, but we just couldn't get them done. Thank you.
For those of you in the room who know me, you're probably not going to be surprised to see that my title includes Africa. And I'm not just talking about Africa because I'm from there, but it really is the next frontier of air quality if you're interested in all issues associated with air quality. So you've probably seen as I've been walking up to the stage, this graphic showing the time progression of the largest 20 cities in the world. And you can see that by 2100, 13 of them are located on the African continent. And the largest cities in China fall off that top 20 ranking. So now that I've sufficiently justified my research, now what we want to do is assess what the energy trajectory will be for Africa, where there is electricity access in many cases of less than 50%. It hasn't undergone the industrialization that we're seeing in many other parts of the world. So it really is a continent of uncertainty, where one large source of uncertainty is rapid population growth. And so what we did is we developed these scenarios. So we have the present day estimate of fossil fuel use from generating capacity and also vehicles, where our present day we call 2012. And so on the left-hand side plot, I'm showing the generating capacity per country, the total for the continent, which pales in comparison to somewhere like the US, which for 2012 is more than 700 gigawatts. And then the locations of the fossil fuel power plants that use either natural gas or coal, where in 2012 most of it is coal. And then we have our future scenario, and this isn't just speculative. These are planned or commissioned power plants for the African continent with this really large growth in natural gas use, because there are large reserves of natural gas on the continent. There are very few reserves of coal. Most of them are located in South Africa. What we do find from this that is encouraging from a sort of electricity access point of view is that the generating capacity does increase by 130%, which is larger than the increase in population from 2012 to 2030 of 54%. We do a bit of a crude estimate of what vehicle emissions will be by just saying that the vehicle ownership will scale by population, because there's a lot of uncertainty associated with this. We're probably underestimating fossil fuel emissions from vehicles because there should be an increase in income per household as the economy grows across the African continent. And so we're probably being a little bit conservative in vehicle ownership. And so what's shown in this slide at the top is the mapped emissions of SO2 NOx and primary PM 2.5 for the present day scenario. And then the bottom is the spatial distribution of the emissions in 2030, showing that where we have this diffuse distribution, it's largely from vehicle emissions, and these large point sources are the power plants. We see that SO2 more than doubles, NOx almost doubles, and primary PM 2.5 doesn't increase as dramatically. Most of it is coming from vehicles, and the emissions don't increase as much as they do for fossil fuels. For power plants. And we then implement the emission inventory in the Geoschem chemical transport model, nested at high resolution over the African continent. And so what I'm showing on the far left is the 2012 estimate of surface PM 2.5 in the model. And you can see that it's inundated with dust. So the Sahara Desert has this really large increase in PM 2.5, contribution of PM 2.5. The middle panel shows the difference. So we don't do anything with the meteorology. We use 2012 meteorology in the model, so we don't confound our results. So the only change that we're seeing here is because of this increase in emissions. And we see a large increase of up to 10 micrograms per meter cubed in the high veld of South Africa as a result of this increase in power plant emissions. And then also in Nigeria, almost central Nigeria, near to Abuja, which is the capital of Nigeria, and also the largest growing city in the world. We also tested what the sensitivity of PM 2.5 is to SO2 emissions, and we found that most of the sensitivity is really in the locations that aren't going to benefit from the electricity generation that will result from this inundation of fossil fuel emissions. For Southern Africa, for example, it's associated with the recirculation pattern that happens there. So the power plants are increasing in the high veld in South Africa, but this air is circulating all the way up to the northern portion of Southern Africa and out over the Atlantic Ocean. So you see this enhancement in Angola, in a country that's not really benefiting from the increase in fossil fuel emissions. And then when we look at something like the TROP-OMI instrument that provides us with very high resolution measurements of NO2 and SO2, we're seeing enhancements in NO2 and SO2 co-located with these recently commissioned power plants. So the circles show present day in our scenario power plants. The upside down triangles show recently commissioned power plants that are supposed to be operating during the TROP-OMI observation period. To the north is Medupi, which is the largest dry-cooled coal-fired power plant in the world. And 2 of the 8 units are already operating, and you can see this enhancement in SO2 and NO2. The other one is Kusile, and I found out from digging a little bit and asking family members that it's actually not operating. So it's a little bit of a downer, but it almost seems like mismanagement and lack of skills to actually repair broken units might actually lead to reduced exposure to fossil fuel emissions, given the scenario that we have for South Africa. And so what we do is we test what the implication will be for health. And so what I'm showing here is just per country what the premature deaths are that are associated with exposure to this PM 2.5. And what we find from this is that there's this near equivalent number from vehicles and power plants because of this co-location of emissions and this increase in population. We estimate the total premature deaths for Africa from exposure to this future fossil fuels of 65,000. And this pales in comparison when you look at a study for India and China, for example, and also in comparison to the windblown dust estimates for Africa, which are almost 1 million. But what's important to emphasize is that these are avoidable. Africa is in a unique position to adopt renewable energies rather than follow the same trajectory that every other developing country has followed, which is this adoption of fossil fuels. And so we're hoping that the study that we've done will further emphasize the switch for the African continent. Thank you very much for your time, and I'm happy to take any questions.
been much more heavily used for nested simulations in Asia and the US. How good is its simulation capacity when it comes to Africa space iteration?
What do you mean by simulation capacity?
So how accurately can we model African air quality today?
It's going to have lots of issues, right? The emissions have sources of uncertainty from the anthropogenic emissions and also from something like wind-blown dust, where we actually did a comparison in this study between the satellite-derived PM2.5 that comes from Dalhousie and then our estimate of PM2.5. And we do find for somewhere like the Sahara Desert, which is the largest source of PM2.5, that we do overestimate PM2.5 from dust. So there are large sources of uncertainty, associated with emissions.
So you're going to electrify Africa, and that's going to reduce the solid combustion. So a lot of pollution at the moment in Africa is coming from the burning of solid.
Yeah.
And so you're portraying this as a negative. If you can move people from using solid fuel to using electricity, that could be a positive.
Yeah, and
so there's a balance here between those two kind of trends. So our work in West Africa shows all of the sources from solid fuel combustion.
Yeah.
And if you can electrify it, that's reducing.
Yeah. We haven't incorporated that in this because there is such large source of uncertainty associated with indoor exposure. So we didn't grapple with that issue. But yeah, that is a potential benefit, is that people do move off of dependence on solid fuels.
That was a question, but then Hannah, right?
Oh, there you go.
I was just curious, do you know if there's any efforts for like
There are some projects, and I think Matt is probably better at answering this than me. Somewhere like Lagos, they have tried to address exposure to vehicle emissions by moving heavily pollutant vehicles outside of the city. I don't know to what degree these have been successful. There are hardly any ground-based observations to be able to evaluate that. But there are efforts at the country scale.
So you get the last one.
I guess I have a similar question. Your analysis, I'm assuming, assumes something about control technologies for SO2, for power plants. We just assume there's.
We assume no control technologies. So we assume business as usual. We don't have much to go on for that kind of decision that we made. South Africa is sort of the area where most of the fossil fuels are burned for power generation, and they're supposed to have control technologies. It's not well enforced. So we just assume no abatement technology.
All right, I think we're all going to take us back to China next, right? There you are. Sorry, I didn't see you.
All right, thank you, Emily. Good afternoon. I'm Vidal Shah, and I'm going to take you back to China, looking at NOx emission trends, but thinking more about NOx chemistry and how they affect NO2 concentrations and trends. Now, Chung showed earlier that NOx emissions in China have been changing rapidly, and this is consistent with satellite observations. I'm showing OMI observations here, which show an increase from 2005 to 2011, and then a decrease in NO2 columns after 2011. But there's an interesting issue here. If you look at Central Eastern China, and we just put the satellite observations and the NOx emissions on the same scale, we see that the trends in the NO2 columns have been steeper than the trends in the NOx emissions. Now, these NOx emissions is from MEIC inventory, but it was true when emissions were rising before 2011, and it seems to be true post 2011. And this isn't just OMI. Other satellite observations also show the same pattern. So what's going on here? We know NO2 concentrations, NO2 columns are sensitive not only to NOx emissions, but also to sinks of NOx. The two main sinks of NOx, as we know, are oxidation by OH during the day, and in the nighttime, oxidation by ozone, which goes on to form NO3, N2O5, which is lost on aerosol particles. There are other loss mechanisms which are not that important in a polluted mid-latitude atmosphere. But the interesting part is that the reactants, ozone, OH, aerosol surfaces, they depend themselves partly on NOx concentrations and on other anthropogenic species like SO2. Now, Chung showed that SO2 emissions have been decreasing even further, even faster than NOx emissions. And we expect that aerosol concentrations must have changed significantly. And there are some studies that have shown that too. So it's likely that NOx lifetime may have changed in the same period. Has it not? How so? And that's a question I'm interested in. So the real question is, has the NOx lifetime changed between 2011, 2012 at the peak of NOx emissions versus present day? And I'll use the geoschem model to answer that, driven by the MEIC inventory for each of these years. And we'll be looking at summer and winter separately. So I'm using version 12.1 with a few modifications to the reactive uptake coefficients of NO2, NO3, and N2O5. Now, these were evaluated against the winter aircraft campaign previously, and they also give results which are consistent with HONO observations over Central Eastern China. These make the most effect in winter when heterogeneous pathways become more important. And overall, they increase the NOx lifetime in winter over China by a factor of 2. So after these modifications, when you compare the geoschem NO2 columns with OMI NO2 columns, we see a really good agreement. For summer as well as winter, we see that the model NO2 columns are within about 20% on average for Central Eastern China. Which suggests that the NOx emissions in the MEIC inventory and the NOx lifetime in the model, they're both reasonable. Interesting is that geoschem is able to capture this factor of 3 increase in NO2 columns between summer and winter. And that's driven by changes in the NOx lifetime. NOx lifetime in summer is short, about 6 hours. It increases by about a factor of 3 to 20 hours in the winter. In summer, oxidation by OH is the main NOx loss process, but in winter, as OH concentrations drop, N2O5 hydrolysis becomes the primary loss pathway. Now, this was for 2017. When we compare it with the simulation for 2012, at the peak of the NOx emissions, we see that the lifetime of NOx in the summer hasn't changed much. It's about 6 hours, remains about 6 hours. And there's some canceling effects, but overall not much of a change. But for winter, the NOx lifetime between 2012 to 2017 has decreased by 20%. Now that's because the loss of NOx by N2O5 hydrolysis has become faster. And turns out it has nothing to do with aerosol concentrations, but it's because of an increase in nighttime ozone during winter. So what we find is as NOx emissions go down, there is less titration of ozone at night by NO that increases the ozone that's around for oxidizing NO2, and the N2O5 hydrolysis pathway becomes faster. We see from surface observations in China that nighttime ozone in winter has increased and at about almost the same rate that is predicted from our simulations. So as NOx lifetime in the winter has shortened, the NO2 concentrations have decreased faster than the NOx emissions. And we see that in the geoschem simulations. We also see that in the OMI NO2 trends, although there are some differences, and we still haven't got a very good handle on NOx chemistry during winter. But if you look at the summer trends, we see that they closely follow the NOx emission trends in the MEIC inventory, which implies that MEIC actually does a very good job in capturing the NOx emission trends over China. Overall, the main message in the study is that when we are inferring NOx emission trends from satellite observations, it is really important to consider how NOx chemistry might be changing as emissions have changed. That's it. I'm happy to take questions.
Do you have any way to assess how well the model represents the NO2 vertical profile?
in China?
Not that I know of. I haven't. No, I haven't seen any data that can use to test the model. We have compared it with surface observations, but that's about it.
I was going to be curious whether there's much sensitivity to errors in NO2 in the upper troposphere.
That's a good point. We haven't looked at that.
I have one more question. How variable is this across the area that you're looking at, right? So I went to Berkeley and Ron Cohen said this changes in Knox lifetime is very variable across the US, city to city. So is it also similarly variable, you think, in China?
If you consider the whole of China, yes. But since I'm focusing on Central Eastern China, which is the heavily polluted with many cities, industries, so it's not that variable in that domain. But if I compare it with Western China, there would be a lot of variation. It would be maybe a completely different picture.
Any other questions? I think we have time for one more. There's another. Right, Joel.
So still not sensitive to NO3 plus VOC in this wintertime context, or VOCs? I would think the VOC concentration might be high enough that NO3 plus VOC would be an important factor here, not just the N25.
Yeah, I mean, that was my first thought too, but I don't find it in the model. I mean, there is this significant other component, which, for NO3 and with VOC, which accounts for about 15% of the NOx loss. So it's not more significant than that, it seems.
More? All right, so our next speaker is Hong Jian.
Okay. Good afternoon, everyone. I'm Hong Jian Wong from Peking University. My supervisor is Professor Jing Tai Lin. Today, I will present how to calculate the global high-resolution emissions for soil NOx, biogenic VOC, and seesaw aerosol, and how to read these emissions in just a model of line. Why global high-resolution emissions dataset is needed? As we all know, the natural emissions of air pollution play a major role in air quality and climate change. So the long-term fine-scale dataset can be used to study the effects of these emissions on air quality, climate, and carbon cycle. Besides, the nonlinear homogenization with metadata of these emissions will lead to the resolution dependence of this emission. For GeoChem users, to modify the uncertainty because of the emission resolution, we run model with high resolution emissions of light to ensure emission consistent at different resolution. The modified to clarity high resolution emissions dataset and rate of light emissions in GeoChem model is simple. We first run chemical standalone model with 2D high resolution metadata. These are the metadata we use to output hourly global high spatial resolution emissions. These are the emission variables we output, including soil NOx, biogenic VOC, and seesaw. We then read these emissions in just a model of light. When running, the chemical will interpolate this emission to the model resolution. Okay, let's take a brief look at our data. For soil NOx, with the season variations of temperature, the high soil NOx moves from southern hemisphere to northern hemisphere. And the season cycle of soil NOx is obvious according to the monthly temperature profile. For BVLC, we take the major shore, ice spring, for example. Ice spring is emitted in the southern tropical region. In July, the ice spring will expand to the hot tropical region. And the season cycle is also obvious according to the monthly temperature. For seesaw, in January, the high seesaw according in Atlantic. In July, the high rise according in the Indian Ocean. But the season cycle of seesaw is weak. In GeoChem model, this emission was calculated online at model resolution. However, due to the nonlinear permutations, the resolution dependence is obvious. Let's take the soil NOx, for example. As the resolution increases, the global total soil NOx increase also. Compared to resolution at 400 kilometers, at 25 kilometer resolution, the global total soil NOx increasing about 22%. Also, the seesaw also increasing as the resolution increasing, but the increasing of the ice-cream is weak. Besides, there are also more detailed distribution information, but for global method, it's difficult to see the influence. So we take the Southeast Asia, for example. Okay, we can see that as the resolution increases, not only the global total soil loss increases, but also there are more detailed distribution information. For example, in India, you can find more distribution information. Besides, the resolution dependence or emissions may be more obvious in some regions. For example, ice spring. Compared to global ice spring, the Southeast Asia ice cream increase as the resolution increasing is more obvious. To modify the uncertainty because of the resolution emissions, we read high resolution of light emissions in the scheme. Let's see the influence if we do so. At 400 kilometers, the difference between of light and unlight is mirror. Because of sub-MO, because of the emissions is a mirror difference. But when we use the high resolution emissions, the sub are not different hues. Okay, in conclusion, we use chemical standalone and general global hourly high spatial distribution emission. And we find that as the resolution increasing, the great total emissions and the more detailed spatial distribution information of emissions. And then we read these emissions of light in GISCAM. And the offline emissions will be included in GISCAM later. So if you have any question, you can ask me or contact us. Thank you.
Lots of time for questions.
So our biogenic NOx emissions just can depend on the nitrate deposition flux. How are we going to deal with this problem in the offline emissions?
Okay. Sorry,
Do you see what I mean?
No, I had no good idea to deal with this one, so we can talk about this.
I can answer the question for you.
Yeah, that would be great.
The short answer is no. We haven't dealt with that problem. The problem has been raised for several times, but we haven't gone so far. But that's a very small impact.
Just small impact.
Yeah.
Yeah. Okay.
Other questions? I think we move on to the posters then now. Oh my gosh. Oops. Sorry, Kelly. Excellent.
All right. Okay. Hi, everybody. I'm Kelly Wells from University of Minnesota, and today I'm going to be talking to you guys about measuring isoprene from space. I probably don't need to convince anyone here about the importance of isoprene. It's the most dominant emitted biogenic VOC to the atmosphere, and it's important in terms of its impacts on ozone and SOA formation, nitrogen cycling, and atmospheric oxidation capacity. And the bottom-up emissions for isoprene span a pretty wide range. Our sort of best estimate for the global annual flux is about 535 teragrams per year, and this is the central estimate from the Megan version 2.1 biogenic emission model. But depending on the model in which you use Megan, you can get a pretty different answer for that global flux. So for example, if we put it into GeoSchem, I think this is version 1102E, you get a global flux of less than half of that central value, just 235 teragrams per year. And this is due to sensitivity of those emissions to uncertainties and driving parameters such as meteorology, land cover, canopy parameterization, et cetera. And while there have been a number of studies that have tried to develop top-down constraints on isoprene emissions using space-based formaldehyde, there are some uncertainties associated with this, mainly that, does this work? Oh yeah. So mainly the relationship between formaldehyde and isoprene, if you can see that down here on the bottom, is varies non-linearly as a function of NOx. Additionally, we know that isoprene is not a unique source of formaldehyde to the atmosphere. So recently there's been some measurements of the thermal infrared absorption cross-section of isoprene that are, that's shown on the right here. We'll be focusing on these two features right around 900 wave numbers. And these are allowing us to start getting direct observations of isoprene from space using CRIS. And CRIS, as you've heard from a few talks today, stands for the Cross-Track Infrared Sounder. The main things to know about it are that it's a scanning instrument with a wide scan width, so it provides near global coverage twice daily. It has an equator overpass time of about 1:30 local time, AM and PM, so this afternoon overpass corresponds well with the timing of high isoprene emissions, high vertical mixing, and thermal contrast. And compared to other infrared sounders that are currently in space, such as IGC and AIRS, in the spectral region of interest for isoprene, CRIS has quite a bit lower noise. So to get at the global distribution of isoprene from this very large data set that we get from CRIS, we use a two-step approach. The first being that we calculate the global distribution of what we call the brightness temperature difference, which is simply the difference between the brightness temperature at the right-hand side of the peak of the absorption feature and the brightness temperature at the peak of that feature. We use the new 28 absorption feature, which is shown on the left here, because it provides better separation from interferences such as water vapor and nitric acid. So we derive a global distribution of this parameter from CRIS, and then to relate that to the isoprene total column, we then train an artificial neural network to do this. And this is what ours looks like, where we have an input layer with 6 predictors, that brightness temperature difference that I'm showing here, along with a nitric acid total column, a thermal contrast, water vapor column, surface pressure, and the satellite viewing angle. The training set that we train our network with is derived using a year of radiative transfer simulations over land, which corresponds to about 165,000 spectra. Those employ geochem isoprene with some noisy scaling applied. Then we take 10 random extractions of this synthetic data set to train the network. Then once it's trained, we apply it in a forward prediction on the measured CRIS brightness temperature difference, along with measures of temperature and water vapor from MERA2 and nitric acid from a CRIS retrieval product. So here's some results over the Southeast US. On the top here shows a map of CRIS isoprene total column for July of 2013 compared to a geochem prediction for the same month. And then on the right here is just the one-to-one comparison between those two. And then on the bottom here, I have campaign average density weighted boundary layer concentrations from 2 campaigns around the same time of year, SunX in the middle panels here, and then Seekers on the bottom. So the 2 things that I want to point out are, first of all, you can see that CRIS really sees that the majority of isoprene in the southeast US is over this Ozarks region of southern Missouri, northern Arkansas, and that coincides with the hotspot that the aircraft measures in both of these campaigns as well. Whereas geochem isoprene really peaks a bit further to the south and with lower total columns. And secondly, if you look at the correlation and slope between CRIS and the model, those values are quite consistent with what you see for the comparison from aircraft to the model. So this gives us some confidence in the spatial distribution of isoprene that we're deriving from the CRIS measurements. So here's what a global distribution looks like of isoprene from CRIS. On the left here are those maps. I'm just showing 2 months as an example here. We have April on the top and July on the bottom for both for 2013, and then comparison to geochem on the right. For now, I'm just going to say that there are some interesting differences and similarities that we're starting to slowly unpack. But lastly, I just wanted to talk about one region, zoom in on the Amazon basin. So on the left here, I have CRIS isoprene total column over the Amazon for January, April, July, and October. And then on the right here, I have CRIS in the black and geochem in the red, total column isoprene averaged over this red box. So first you can see that CRIS isoprene column tends to be lower than the model throughout the year, but particularly in July. And then if you overlay some in situ measurements that were taken in the vicinity of this white dot here, you can see if you look particularly from July to October that this large increase in isoprene between those 2 months that Chris sees is pretty consistent with what those in situ measurements suggest. So it turns out that at this time of year, July, you tend to have this transition period in the Amazon between the wet season and the dry season, where if you can see on the bottom here, the timeline of LAI, you tend to have low LAI at this time of year due to a dominance of younger leaves, which emit relatively little isoprene versus mature leaves. So you get this drop in isoprene, which then increases again as you move into the dry season. So, and of course, the model does not capture this very well. So this is just one example of, the types of things that we're starting to see with this new data set. So we look forward to doing more work with all of you. Thanks.
Questions for Kelly? She has extra questions because I messed up.
So in your comparison with aircraft measurement,
Yeah.
the aircraft is not go very close to the ground, and actually it's very short lifetime. So you obviously have to do some extrapolation of the critical profile of isoprene. I wonder how much will this affect the comparison?
Yeah, so we try to do the best we can with that. We limited the comparison to just measurements below 800 HPA, and then also at roughly the same time of the Chris overpass, within a couple of hours. But yeah, that certainly is a limitation of using the aircraft, yeah.
So, has there been any work going on trying to use some of this new Chris-derived isoprene data set in order to try to optimize the negative model used in GeoChem and try to get rid of some of that mismatch? Because from what you showed on one of your last slides, you can see that the Chris data looks like it's primarily being driven, the seasonal cycle you're seeing is driven by changes in leaf area index. So is there a way possibly that you could use some of this Chris data to try to improve how those driving factors are represented in MEG and in GeoChem?
Yeah, for sure. We have not done that yet, but that would be the hope.
So, Karen, you previously showed that at least in this part of the country, there's a pretty strong resolution dependence to isoprene. And I'm wondering, especially as we're moving to high resolution inputs for all of the model runs, whether you thought about doing this validation work at a higher resolution for North America?
Yeah, that would be great. One of the downsides of, so Chris measurements have relatively low noise, but we still have to do quite a bit of averaging to get a good signal. So we'd have to see what the trade-off is with going to higher resolution.
I'm just curious, like what motivates the use of neural networks in this case, compared to like a simple baseline, like multilinear regression or equilibrium?
What motivates the use of the neural net? So it would.
What is compared to like a simpler, more common baseline, like linear regression?
So we tried doing some multiple linear regression, but it was pretty clear that it wasn't capturing the relationship between these 6 predictors and isoprene very well. So that was the motivation to moving to the neural net. But the motivation for using the neural net in general is that because this is such a large data set, it's difficult to do a more computationally involved retrieval method, such as optimal estimation.
Questions? All right, then we, go ahead.
I might not be thinking about this like clearly enough, but it's not obvious to me that a direct measurement of isoprene is that much better than a direct measurement of formaldehyde to retrieve or to like get emissions, because formaldehyde is the oxidation product, but isoprene's lifetime will also depend on the chemistry. So we're still stuck with the not knowing the chemistry that well when you retrieve or try to get emissions. Do you know what I mean?
Yeah, so the distribution of isoprene, it looks like emissions in some places, and in some places it doesn't because of the variation in the lifetime, right? So, you can, ideally you would combine information between the two to get at both of those.
All right, so now we move on to posters. Hurry up. All right, so you're gonna line up. Yeah.
Do the secret You can come up. You can line up in the secret entrance.
Hi everyone, I'm Nanling from Tsinghua University, and in the recent years, Chinese NO2 emission from a positive trend to a negative trend, and in this study, we use the OMS satellite data to identify the turning point of the NO2 emissions in China. The geochem is used to remove the meteorological factors. Welcome to the A22 posters for more information. Thank you.
Louise had a full loss, so we're gonna do it till the end. Didn't you? No? Oh, all right, we're stopping every time.
Hi, I'm Jean from CU Boulder. Formaldehyde has been underestimated in East Asia in recent years by about 50% compared to aircraft and satellite retrievers. We worked on estimating top-down emissions of NMVUCs, sources of formaldehyde, by using HRD finite difference mass balance, which is much faster than 40-bar inversion, as introduced by Chi. So please come and see at A23.
Hi, I'm Tina. I'm a graduate student here at Harvard, and on my poster, I'll be presenting on diagnosing the spatial biases and uncertainties in global fire emissions inventories with a focus on modeling PM2.5 in Indonesia as our regional case study. As part of our paper, we developed an online tool called FireCam, which you can access here at the link. And if you're interested in how the choice of an inventory can affect your modeling results, please come by my poster at A24.
I'm Luke Schiffer. I'm a postdoc at Columbia. I've been looking at carbonyl sulfate, or OCS, which is often used as a tracer for carbon uptake. If we reduce the uncertainty in the budget, we are hoping to improve its application for this purpose. So far, we've implemented in more recent anthropogenic emissions, which improves representation of the model over Pacific outflow regions, especially from China. If you're interested in OCS or other GPP proxies, please come talk to me.
John Wang here. So this work is motivated by one of the studies that we did a couple of years ago, which showing that the moderate NOx, solar NOx emission is much lower than observed NOx emission in the places that temperature is very high and agriculture is dominant because of the. So we show that in the geochem model, we improve the parameterization by improve the dependence of the solar NOx emission as a function of temperature, especially high temperature. Also, we added the soil temperature into the model. So check out.
Okay, so we updated the dry deposition parameterization in NO2 in two ways. First, in green, reduce the resistance to surface uptake of NO2 by representing its hydrolysis on the ground surface. Second, in blue, develop the parameterization to account for the underestimate in dry deposition of NOx. And a main result is increased net deposition of NOI close to NOx sources. Thanks.
I'm Arshad Nair, grad student at SUNY Albany. So motivated by the recent evidence of the importance of ammonia in atmospheric new particle formation and its increasing trend in several parts of the globe, I examined geochem simulated ammonia with ground-based network and satellite remote sensing measurements. So I'll be discussing some of my findings from this model observation comparison, and I look forward to your inputs and suggestions on the role of emissions, chemistry, and inherent issues with these measurement techniques at A28. Thank you.
Hello, I'm Jin Boma from SUNY at Albany. So ship tracks are clearly showing in the global SO2 emissions. What happens in these ship rooms, especially nonlinear chemistry and also microphysics. For example, particle number
So in order to understand this question, we couple the NCAS box MOX photochemistry box model with APM, and we found that the number of particles formed in a shape room at different times of the days differ significantly. If we want to know more, welcome to survey my poster 28. Thanks.
Hi, my name is Carmen Lemkuzla. I'm a grad student at the University of Connecticut. I've been working on a source apportionment tool for GeoSchem, and it's actually working and producing cool stuff. So yeah, it lines up pretty well. If you're curious to sort of see some of the things we've started doing with it, or some of the things we plan to do with it, or just sort of curious what role source apportionment could have in GeoSchem, I'll be at A30, and yeah, I'll hopefully see you then.
Hi. Extreme forest fire events can trigger thunderstorms that can inject smoke directly into the upper troposphere and lower stratosphere. We call these pyrocumulonimbus. One of the largest of these events took place back in 2017 in Western North America. In recreating the event in GeoSchem, we found with stratospheric injections that the model can recreate the spatial and vertical satellite observed distributions. And we also found some interesting results when we coupled this with a radio transfer model. Thank you.
Hello, my name is Amy Bonilla. Indian glaciers are melting, and this can be seen on the picture on the left, where I have plotted the percent loss of glacial surface area since the 1960s in the sites in Peru. Here on the right, I have GeoSchem results that show that black carbon enhancement due to fires in September 2014 reached the Andes in southern Peru and Bolivia. So my main research question is, what are the influence of smoke on either regional climate or snow melt in the Andes? Thank you.
Hello everyone, I'm Yang Liu from Tsinghua University, and in this work we use the GeoSchem joint model and input-output model to analyze the ammonia emissions embodied in the international food trade and their health effects, and our results shows there are about 600,000 premature deaths is caused by the ammonia emissions, and 16% of this caused by the international caused by the consumptions in other regions. If you have interest, please find me at the 1.33.
Sure. Yeah, it's much better that way. Okay, I want to thank all the speakers for very illuminating presentations and for keeping the time. And I want to thank the session chairs for making sure the speakers kept the time. So now we're moving on to the more interactive part of the day. We're going to have 2 sessions of model clinics. There's going to be a clinic here on working with GeoSchem. That's more for beginner and intermediate users. There's going to be a clinic on the new Wharf GeoSchem facility developed by Chung-Mei Fu's group. And that's going to be in Maxwell Dworkin. And there's also going to be an organizational meeting of the Stratospheric Working Group. That's also going to be in Maxwell Dworkin. I refer you to the agenda of a precise room. After this, there's going to be another clinic on GCHP that's going to be here. And there was a lot of demand for that clinic. So therefore, we're not planning any sessions in parallel to that. After that, we're going to have working group meetings. And again, let me insist on the importance of those working group meetings for you to figure out what the latest is with the model, what are the problems that we're presently dealing with, to set your own development priorities. We're really looking forward to your input on this. So we're going to have 3 working group meetings in parallel. And then at 6 o'clock, we're going to have our poster session in Maxwell Dworkin together with refreshments and a dinner buffet. Just at a small point, the rooms in Maxwell Dworkin, G115 and G125, for those of you who remember, those are the rooms where we met in previous times. Those are ours to use until 5 o'clock, and then there will be extension school classes. So if you are using those rooms, if we have clinics in those rooms, just make sure you vacate out there by 5 o'clock. With this, pick where you want to go, and I look forward to seeing you all at least at the poster session at 6. Thank you all.